In the last video, we saw that if we had an infinite series where each term is a function of n, and the function itself is a continuous positive decreasing function over the intervals that we care about, and we assume that this series converges, then we can estimate that series, we can just estimate that value that it converges to using a finite number of terms and some integrals. And the way that we establish these integrals is because when we split up the sum into a finite sum and then another infinite series, we're able to conceptualize that infinite series in two different ways. It could be an underestimate of this integral right over here, or it could be an overestimate of this integral right over here. And because of that, that allowed us not only to estimate s, but to put bounds on it. If we can evaluate the left-hand side here and the right-hand side here for a given infinite series, then we can establish our bounds on s. And so let's see how good these are by applying it to a particular infinite series. So let's say that the infinite series we want to apply it to, let me do it in the yellow color. So it's going to be, let's say we go from n equals 1 to infinity of 1 over n squared. And let's say we didn't know how to find the exact value here, but we want to estimate it. And let's say we want to estimate it using the first, let's say we want to estimate it using the first 5 terms. So we'll do s sub 5 is equal to the sum of n equals 1 to, n equals 1 to 5 of 1 over n squared. And let's see, this is going to be equal to, let's get a calculator out. This is going to be 1 over 1 squared, which is just 1, plus 1 over 2 squared, which is 1/4, plus 1 over 3 squared, which is 1/9, plus 1 over 4 squared, which is 1/16, plus 1 over 5 squared, which is going to be 1/25. 1/25. And we get this value right over here. So I'll just say that this is, I'll say it's approximately 1.464. Approximately 1.464. And then let's evaluate each of these integrals. So our k in this case is going to be 5. I just picked that arbitrarily. We could probably get a better, or we would get a better estimate if we had a higher k, if we did the first 10 terms or 20 terms, and we would have a worse estimate if we did k equals 3. But I just picked k equals 5 because it seems reasonable, something that we could compute. I actually didn't need a calculator to do that. I could have done it by hand. It would have just taken more time. But let's evaluate these integrals here. So the integral from 5 plus 1, so it's 6 to infinity of 1 over n squared dx, and let's see, that's going to be equal to, let's write it this way. This is going to be the limit. Let me do all of it in blue actually. This is going to be equal to the limit as let's introduce a new variable. B approaches infinity of the integral from 6 to infinity of 1 over n squared dx, which is equal to the limit as b approaches infinity of, let's see, the antiderivative of this is negative n to the negative 1. And we're going to evaluate that at b and at 6. So this is equal to the limit as b approaches infinity of negative 1 over b minus negative 1 over 6. So plus 1 over 6. Well, as b approaches infinity, this term right over here goes to 0. So this is just going to be equal to 1/6. And we can use that exact same logic to evaluate this integral. So let's do that. Actually, so I'll do it right over here. So the improper integral, I should say, and here we're going to evaluate not from 6, but from 5. That's our k. 5 to infinity of 1 over n squared dx. Well, the only difference here between these two integrals is this bottom bound. This was 1 over 6, and by the same arguments, this one's going to end up being 1 over 5. And so now we can put everything into this compound inequality. We're going to have 1.464 plus, and this is, I'm being a little bit approximate here, it's really this s sub k, which we have the exact value for in our calculator. So it's 1.464 plus 1/6 is less than or equal to is less than or equal to our sum, which we care about, which is less than or equal to 1.464 plus 1/5. And so this one is fairly straightforward to calculate. This is going to be plus 0.2. So this is going to be less than or equal to, let's see, 1.264. So sum is going to be less than or equal to that. And on this side, if we took our original expression and then I added 1/6, I get let's see, what did I, oh, this is supposed to be I wrote this one wrong. Okay, so this is going to be 1.630. Let me just write 1 point. So it's going to be 1.630. And on this side, my brain was malfunctioning. This should be 1.1. I took away 2 instead of adding 2. 1.664. 1.664. And so just like that, you see, okay, this thing must be like 1.6. It could be 1.63 something, it could be 1.64 something, it could be 1.65 something, it could be 1.66. But this is already giving us a lot of precision. If we only cared about things to the tens place, we're done. We know it's going to be 1.6 something. And if we would go a little bit further, this is already giving us a lot of precision. And you can imagine, if you added a few more terms in the partial sum, you would get even more precision. So hopefully you found this to be kind of a neat exercise. Not only did we get a good bit of precision with just taking a partial sum and the help of these integrals, but we got a good bound on it. We know that the sum that we're converging to is between these two values.